Moffett Field. And Ray has been applying networking technologies in novel ways for the last few years, including remote science in locations as remote as southern Chile, northern Canada, and most recently in space and satellite communications. The SmallSat and the related missions provide platforms for technology demonstration, and they're also an inspiration and experience for students and interns from a variety of institutions. So in that sense, I think it's a really neat dovetail that we're getting to see a report of some of their recent activities. So please welcome Ray Gilstrap.
And of course, all the pop-ups that I was not wanting to have pop up are all there now. Okay. All right, so good morning, and thanks for coming. So, as Mark mentioned, I'm Ray Gilstrap. I'm out at NASA Ames, and so we're going to talk a little bit about some of the work that we've been doing with demonstrating novel communications technologies in a series of SmallSat missions that we've been working on for the past few years. So this is the overall program that we're dealing with is Small Payload Quick Return, SPQR, which if you happen to be a student of Roman history, you know there's another meaning to that as well. Okay, so just a quick run through the things that we're going to talk about, a little bit of background, a little bit of details on some of the missions, and then I'll spend a fair amount of time talking about our most, well now, what was our most recent launch up until a couple of weeks ago, and some of the technologies that we flew on that, and then I'll wrap up. Okay, so just as a little bit of background information, so there's been a lot of interest in small satellite missions, nanosats and picosats, you know, just kind of depending upon what the size of the craft are. And the nice thing about those is that it enables you to get some good science done at very low cost relative to you know, missions to like the billion-dollar satellites you know, going to Mars. And so if you happen to not have that kind of a budget around, then looking at these smaller satellite buses is a good way to either get some science done or prototype new technologies in with a much lower risk profile. And so the nice thing about the capabilities of these satellites is that they've been increasing over time as you know, hardware has gotten faster and processing has gotten faster and more, and communications has gotten better. So you can actually do a lot of good work on a very small platform with a very modest budget. Another nice thing is that it also enables rapid prototyping. So, you know, if you have an idea for something you'd like to do, there's a lot of kind of off-the-shelf components that you can plug in, some modular buses you can attach things to, and a number of launch opportunities out there that you can take advantage of. You can actually get something from the back of the envelope or the napkin into orbit in pretty short order. So at Ames, we've been working in this area in quite a while. There's been a pretty solid effort on it over the last 10 years or so to really push the envelope in terms of what we can do in small sats, and both in areas of CNDH, communications, avionics, and novel mechanical systems. So we'll touch briefly on some of those. So the overall goals that we've been reaching for are you know, evaluating new technologies, you know, getting some actual work done on the cheap, establishing flight heritage for new technologies, so things that we think might be applicable to larger scale missions or longer duration missions, but they might not want to, those missions might not want to risk trying out a technology that doesn't have a lot of flight heritage behind it. And so this is an opportunity for us to provide that flight heritage. And at the same time, we also establish collaborations with other folks that are operating this space. And there are a number of institutions out there and organizations that are interested in this. And so we've put together a number of good collaborative partnerships and gotten some good work done with that. Just so you know, it takes a village to raise a spacecraft, and so these are some of the folks that we've been working with in our most recent series of demonstrations. And So it's been actually a very good partnership. So just a quick run through of 3 missions that we've been working on kind of jointly. One is called Phonesat, and so it's a small sat that uses just a regular old cell phone as the processor for doing the command and data handling. And this is something that began as a summer student project a few years ago, and has kind of evolved over time, and capabilities have evolved over time. And so I think we're up to the next one that's going to launch is Phonesat 5. And one of the things that has come out of this work is that it's demonstrated that just commodity hardware can actually work pretty well in the space environment. So I have a couple of pictures here of, I think that's Phonesat 1 on the left, and we're looking at a CubeSat bus, which is a 10-centimeter cube, and all the electronics are inside. That's a complete self-contained satellite, and there's an antenna that's sticking out of one side, which is a tape measure, and it's hanging from a high-altitude balloon. And on the right, we see some of the photos that were taken with the cell phone camera off of Phonesat 1. The next series of missions is called TechEDSat, or Technology Education Satellite, and that's a collaboration that began between Ames and San Jose State a few years ago. And that's a series of CubeSat missions, sort of with different capabilities depending upon the generation of TechEDSat. But all of those, what they have in common is that they're all launched from the International Space Station. And the focus of most of the recent TechEDSat flights has been for testing out this SPQR concept, deorbiting from. So the idea is that we want to be able to deorbit small payloads from the space station without waiting for another expensive Soyuz launch to go up there and get stuff. So something that you can put inside a small container and pitch it off the side of the station, and there's which essentially amounts to a parachute that's called an exobrake that allows for low-speed deorbiting of the spacecraft, or of the sample, at a rate that will cause it to not burn up in the atmosphere. As the prelude for technologies that go onto TechEDSat, we've also been doing a third series of missions called Sorex, suborbital aerodynamic reentry experiments, and that's a series of sounding rocket launches that it's been going on for since '98, and that's been used as a test bed for testing out a number of entry, descent, and landing technologies, most recently including the exobrake, and also I've been testing a number of communications technologies on that. And so the idea there is that it's kind of a TechEDSat light, in the sense that it gives us sort of a lower cost and more frequent set of opportunities to launch technologies into orbits like in the 300-ish kilometer range, and give us an opportunity to prove stuff, prove technologies that think will work, and then the ones that are most promising will go into the subsequent TechEDSat mission. So the most recent, second most recent now, as I mentioned, was SOAREX 8, which was launched on the 7th of July of last year. And so this was a case where, so the exobrake parachute that I mentioned had been tested on some previous missions, but only at 1/10 scale. So this was, SOAREX 8 was the first opportunity to do a full-scale exobrake deployment, and by full scale, I mean, I think it's total things like maybe 3 meters across. Okay. And so that's basically enables the drag, and so we were able to actually get some full flight data, and I'll show a slide in a second that shows kind of the whole mission profile, and we were able to basically get sort of a long-term test of the full-scale exobrake, and verify that it actually does what we think it's going to do. And at the same time, so the part that is we're going to go into a little bit more detail here on is testing out these avionics and communication systems. So a couple of words about sort of the overall high-level objectives. One is exploring what we call Wi-Fi for rockets. And the idea there is that we want to be able to downlink data from the spacecraft at a high rate and at low cost using commercial off-the-shelf hardware, and using traditionally for CubeSats, what folks have been using is radio from a company called Microhard, and that's been doing well. There's a long history of folks using Microhard radios, but we wanted to increase the bandwidth and we also be able to have a little bit more flexibility in terms of what we can do with the data once we get it down to the ground. So being able to run data over AO211 has been proven helpful in that regard. So the second thing that we wanted to demonstrate was use of wireless sensor networks in space. And so the idea there is that one of the things that is a driving cost or driver for the cost of space missions is launch weight. And a lot of the launch weight for spacecraft is copper wiring that connects up the vehicle subsystems. And so we had an idea a few years ago of, hey, well, maybe we can look at low power wireless networks as interconnections between sensors and the hardware that is a downlink, and that will enable us to save on that copper wiring and save on launch weight. And so we have looked at deploying ZigBee networks in particular, and there have been a couple other technologies that different folks within NASA have looked at, but ZigBee is the one that we focused on for robustness and fault tolerance, and we'll have a little bit more to say about that in a second. And another thing that also have been starting to work on is developing a low-cost X-band downlink for even higher data rates. So this is the part that there will be a quiz on later. And so I know this is maybe a little bit of an eye chart, but basically just gives an overview of the components there. So the key things that we have are sensors. On the right side, we have temperature and pressure sensors, and an IMU, inertial measurement unit, and that basically measures the orientation of the spacecraft. And those wirelessly transmit to an Arduino board that's running what's called an XBee. So XBee is a particular implementation of the ZigBee protocol by a company called Digi. And so the sensors are connected to XBee transmitters. There's an XBee gateway on the Arduino board that receives that sensor data, and then transmits it to the ground using the Iridium Short Messaging Service, which we'll also mention. And then at the same time, we also have a second payload, which is the latest iteration of the Phonesat hardware that also includes a sensor network sniffer and the Wi-Fi subsystem. And so the data from the sensors is also being sent over the Wi-Fi. That's the data that's getting sent over Wi-Fi back down. And there's also a secondary Iridium transceiver for that. So does that make sense? Yes, no, maybe? Okay. And just a little bit more detail about all the RF links we've got. So we've got the two Iridium modems that are sending data to the Iridium satellite network. We've got a C-band transponder that corresponding ground station at the Wallops Flight Facility in Virginia is using to track the spacecraft. Then we have the X-band receiver and then the Wi-Fi receiver. And the sensors, so the sensor locations themselves, so that's the big rectangle here is the Sorex 8 payload bus itself. And so we have a set of temperature and pressure sensors that are where it says XB1 down there at the bottom. And then the XB2 is another set of sorry, back up. And then there's also mounted on the bus is the IMU, the orientation sensor. And then the XB2 is actually mounted on the exo brake itself. And so we get a nice set of numbers on how the spacecraft and the exo brake are moving relative to each other. So for the flight profile, from launch to splashed down in the ocean, and this was a payload that was not recovered. It was about 10 minutes or so. And you can see the different components of the rocket there. And so the experiment is the second thing from the left. And so we had it. There's a range safety issue that the folks that operate the launch facility at Wallops want to make sure that we don't have any stray radio transmissions interfering with their launch. And so we had an altitude sensor in there that kept power turned off to our hardware until it reached 20,000 feet, which is, it took about 20 seconds after that. So over the course of the mission, I mentioned that we were sending telemetry out over the Iridium satellite network. And so because the thing is spinning and it's kind of unclear, the orientation of the spacecraft relative to where the Iridium satellites are located it's kind of hit or miss in terms of when we get the downlink, when we get the data from the satellite. So, or when the data is actually able to reach the Iridium satellite. So we ended up getting just a couple of packets over the course of the mission. However, for the Wi-Fi link, that one actually ended up, we were able to receive signal for the entire duration of the mission. And we had a video camera that was attached as well that also was downlinking data to over the Wi-Fi link. And so we were able to receive that signal once that camera went live. So, as I mentioned earlier, Wi-Fi is particularly useful for low-cost missions. And so we mentioned university-led here because there's so for the federal government use, there's some restrictions on government use of unlicensed RF spectrum, and so we got some we had to do some coordination with our spectrum manager at NASA Ames, and basically on an experimental basis, we were able to fly this. And but for any sort of subsequent missions, I mentioned that we had some university partners earlier. So the university partners basically need to be the operators of record for that payload in order for us to legally be able to do this sort of thing within the FCC and NTIA rules. So going forward, we'll continue with partnerships, with the academic institutions, primarily San Jose State and the University of Idaho, and hopefully we'll get some more research done as to what the capabilities are that we can bring out of this. So for the Wi-Fi link, we ended up going with 802.11b just because it's simple, low rate, and well understood. And so we picked just a couple of USB dongles that were. We did a little bit of testing to try to identify a couple that are robust and. With respect to temperature and vacuum, and deploy those both on the spacecraft and on the ground. The Wi-Fi link was downlink only, which eliminated a lot of complications because we just had essentially it's like UDP, right? So you just send packets out and hopefully somebody will receive them, but you don't have to deal with acknowledgments and that kind of thing. That greatly simplifies the work. So the video that we sent out was VGA resolution 5 frames a second, and running RTP. And we used the dishes at Wallops provided pretty good gain, so enabled us to get both track the spacecraft with the larger dishes that I mentioned, and get a good Wi-Fi signal as well. And one thing that ended up coming out of it, which we did not set out to do, was actually ended up inadvertently setting a record for the longest Wi-Fi transmission at 385 kilometers. And so, we nosed out a previous record that was done in Venezuela. And then we also, so that 385 kilometers is both a combination of altitude and range distance from the dish. And so the altitude that we reached was a little bit over 300 kilometers. And so even at that altitude, that's still a record in terms of highest Wi-Fi link. So on the ZigBee side, So it's a low power mesh routing protocol, and based on the 802.15.4 MAC layer. And as I mentioned, it's something that we think could be useful for interconnecting spacecraft subsystems wirelessly, and resulting in a reduction in launch weight and cost. And so, again, as I mentioned, we use modules from Digi, temperature, pressure, and IMU, and yeah. So if you remember what was in the picture, then these are the words that go with the picture, and so for as far as we've been able to ascertain, this is the first use of ZigBee in space, and so there have been some other folks in the agency that are interested in the work that we're doing. Have done a little bit of stuff in terms of characterizing ZigBee. This is the first time we've had the opportunity to actually fly it. So then on the Iridium side, which is actually another first, so how that works is that the sensor data that comes in on the XBs gets packaged up by the Arduino board into a series of text messages. And so when it is able to establish a link to the Iridium satellites, then it sends that text message out, and then the Iridium network takes that, and once it gets downlinked to the ground, the Iridium ground station will take those messages and package them into emails that get sent to whatever email address you designate. And it makes for a very nice way to just receive the data without having a lot of specialized ground station hardware. The email can be, you can extract the telemetry data out of the email and process it however you like. And you use an email alias to distribute that to multiple recipients. And it makes for a pretty clean solution that's simple to implement. So only the downlink was used for this flight, and there is the opportunity to, or there's a mechanism for going in the reverse direction. You send an email to a special address, and then the Iridium network will broadcast that back to the spacecraft, but we did not use that for this flight. That's something that is on the table for future flights. Come on. Okay, so my computer has had a brain freeze. So I promise that there's more. PowerPoint is to say that, yeah, so with the, so we talked about Wi-Fi, we talked about ZigBee, we talked about Iridium, and so, which is the, and so those things are really the, the crux of the useful data that we got out of there, out of the Sorex mission was, Sorex 8 mission, was that, technologies all work together. And, the nice part about it was we were able to, yeah, the nice part about it was that we were able to kind of pull all those together, like again in pretty short order. And we had different teams that were working on the the different technologies, and everybody was able to kind of integrate everything and get get a fully functioning unit together in time for delivery to wallops and flight qualification testing. And yeah, so apologize. As I mentioned, that the rapid prototyping practices enabled enabled folks to quickly develop their individual modules and bring them together. And also, we had teams that were geographically dispersed, and so using, especially like for developing the software, the flight software itself, folks were able to use tools like GitHub and other collaboration tools in order to effectively develop things jointly, even though everybody was scattered around. So, just in conclusion, I've mentioned we had several firsts in terms of technology demonstrations in orbit, a record distance for the Wi-Fi link, and our experience has been that small sats are great test beds for testing out new technologies, and we're planning to continue to do some more. So our follow-on work, we had SOAREX 9, which just launched a couple weeks ago, which has kind of a second generation of wireless sensors that are smaller in size and power. We've actually moved on from the smartphone. For Phonesat, we've moved on from smartphones to Intel Edison-based processor. And you can still claim use of Phonesat because we're still using the Iridium network. And so we're going to do some more tests. We did some more tests on the Wi-Fi. And so we're still analyzing the data that we got out of that. And so if you want to find out what happened there, you'll have to just come back next year. Coming soon, more missions and just continued evaluation of new technologies. So with that, I want to show I think I have a second to show a quick video. Yeah, my friend will be happy I remembered her birthday, but mad that a whole room full of people knows how old she is now. All right, so this is the launch of SOAREX 9, which just happened a couple weeks ago, as I mentioned. So thought I'd just throw this in. This is hot off the press, and so forget the sound quality, which is an artifact of how the video was. This was a Ustream video that we recorded to a little clip, and so I'll just show a couple minutes of what we saw.
Where was the launch?
The launch was at NASA Wallops Flight Facility in
10,
Virginia.
9, 8, 7, 6, 5, 4, 3, 2, 1, mark. Plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
We have second stage Orion ignition. We have second stage burnout.
So the window that's changing up there with the psychedelic look right now is the video camera.
The ISM link.
Copy, M&O.
We're also seeing some data coming down from the wireless sensors.
You can see on the screen there an onboard camera that they're checking out on this vehicle and showing you the limb of the Earth as the rocket flies.
So you can see, right, get up pretty high, pretty fast. So. All right, so any questions?
Yeah, do we have any questions for Ray?
Yeah, sorry for the technical difficulties that we just proved
Okay,
that.
well, thank you very much, Ray.
Mm-hmm.